Hello guys, and welcome to the next video on our journey of learning OpenGL. Today we are going to continue working on what we left last time. It's been a day now and I've been thinking of maybe upgrading to start programming real game, but since we don't have much experience, yes, we are going to continue learning. So today we are just going to continue where we left off last time. So let me just open my CLIM. And as you can see, guys, today I'm on my Windows machine. So I've already cloned the project on my Windows machine, and I will just be continue coding. So just give the time to my CLion to start. Actually, CLion is actually a great text editor. Is a full ID. It's a full ID where you can find a text editor, a compiler, and a debugger. So let me just open first. Yes, first OpenGL game. And on Windows, that's what I'm using. I haven't paid for it. I've just downloaded it last weekend, and I'm just using my 30-day trial. So when my 30-day trial will end, maybe I will go to VS Code because I don't have money to pay for a text editor right now. But I'll go to maybe VS Code, or I will stick to my Linux machine because on Linux I do code in Vim. So guys, last time this is where we left off. We managed to properly display a triangle on the screen, the proper pink color. Last time I said yellow. Actually was a mistake, my bad, I'm sorry, but it is actually a pink color. So we are going to continue from there. Let me just see if I can compile the code so that, yeah, this is it, you can see. But I've noticed something weird, guys. On my Linux machine, when I ran this code, I was at 16 FPS per second. So the amount of work, the amount of time the game loop iterates each second was 16 times. But on my Windows machine is about, I don't know, 1, 2, 10. Like, I don't know if you can see this. Yeah, this is like, as I'm holding the screen like this, is at 0.25. So I don't know if it's on my machine. So guys, if you can clone the code and try to run it on your machine, maybe that will help debug the actual program. But today we are just going to continue where we left off. And as you can see, I've abstracted away this function, create shader, because I noticed that down here when we were creating the vertex and the vertex shader and the fragment shader, it was pretty much the same code. So I just abstracted that out, and I managed to make the code keep running. So you can see the function here. It takes a shader and the name of the shader program, create a shader with a proper shader type, then it put the source code into the shader and it compiles it. So maybe here's calling it string is not the proper name. We are going to call it source. Okay, we are going to call it source. And now we want to continue where we left off. Let me just open my terminal. I will try to see if I can get the link. If I can get the oops, sorry, my bad. It's clear host. Let me get. Actually, when I'm on Windows machine, I do use PowerShell on the terminal. So, like, I don't know how to use Bash on Linux and PowerShell on Windows. So let me just get this. Okay, this link thing, I have to open it. Let me just do this. Yes. to go. It's not blaming me. I think this is what I will do. I will get the content of the, yes, and this link, actually I can click on it. Okay, this is the link of the book we are reading. One subscriber, one follower suggested me that I should increase the size of the window so that you guys can see. Sorry if the previous tutorial was not clear, but I think right now it's okay. If it's not okay, or if you find any problem, just tell me, leave it in the comment section below. I will check it out, and next time I'll upgrade it. In the first video we did, we managed to put on the screen a simple triangle. This is this yellow triangle. Last time we extended the initialization, so we made error reporting, proper configuration of OpenGL. Today we are going to look into shaders. So we've already looked into shaders when we did buffer and vertex and fragment shader. This is it here. This is it. This is actual shader code. But we are going to look at it in more details. So we are going to click. And guys, the first thing I want to do is that this code does not belong to this main file. Like, for those of you that are used to do web programming or mobile programming, you know that the main file is where you orchestrate all the logic in every other module that you have in your application. So what I want to do first is that I want to take this code, this string, because this is a simple string. I want to take it outside. So I'm going to go maybe in the source. What I'm going to call it? I will create a directory. No, here. I will create a directory called maybe shaders. Oh god dang. This is why I don't like. I do not like Windows because it's too damn slow. Okay. I'm going to call the directory shaders. In the shaders, I'm going to create a file. What I'm going to call the file, I'm going to call it vertex shader program. What is the extension of a shader file? What is the extension of a vertex shader program file? Let's see what VSH. It says the most common extension for a vertex shader program is a .vert. Other widely used extension includes VSH. I'm going to go with VSH. I want to add it to GitHub. So there's a plugin for that. Let's see if I can install. Looks like CLion actually help us here a lot. Okay, while it's downloading, let's go to the book. Okay, it says here that shaders tell OpenGL how to draw, and we have a lot of creative opportunity to do interesting effects. We'll cover the what to draw, the geometry, and more detail in the following article, like what to draw on the screen, the geometry of the drawing, what are other things that we can do with it. Okay, yeah, it's finished. Maybe I will install this too. Maybe all of them. Yeah, all of them. Like, I don't know what extension fits well, but I'm going to install all of them. Okay. Overview. Shaders are mini programs that define a style of rendering. Mini program that define the style of rendering. Okay. They are compiled by a special shader program compiler and run on the specialized GPU, graphic processing unit. The GPU is built to do lots of floating point operation in parallel at once. So it takes a lot of floating point, real numbers, and make some operation on them in parallel, like adding, multiplying, dividing, and etc. Many more than your CPU can. Yeah, actually, you should look up the statistics for your particular GPU's float 32 operation per second and compare that to your particular CPU model float to get a rough idea. Many of the tasks in computer graphics fall in the categories of embarrassingly parallel programming. Setting the position in our scene for each vertex point in 3D shape. We do this with the vertex shader, setting the color of each pixel-sized piece of shapes we render. We do this in a fragment shader. So for position, we use vertex shader. For color, we use fragment shader. Casting and reflecting each ray of light in a ray trace scene. It's possible to do this, for example, in a fragment shader. So this ray trace scene is like ray tracing. It's something that I will definitely look into it later. Ray tracing in computer graphic. Like this is ray tracing actually. Let me just take a picture. Yeah, this is ray tracing. Like taking a source of light, hitting a target with a source of light, the target will reflect. It works exactly the same as the sun does for us. Like when the sun sends his lights, those light hits our body and our body reflects colors. That's how we are able to see things in a regular basis. So, and we can do it in OpenGL too with this ray tracing. Yeah, what a GPU can also do is that it can calculate the physics of individual particles. Maybe for fluid simulation, it's possible to do this using another type of shader called compute shader. I think compute shader will be shaders that are dynamically produced. Because when we look at shaders, like they are like, as we did last time, for points, for positioning our 3D shape on the screen, those points are already calculated. They are calculated by us. But what about like for fluid, for example, or for terrain rendering? Those shaders they are dynamically loaded into the GPU first, and they are dynamically adjusted. They receive some operation on them, and that's how we are able to get a beautiful rendering on the screen. So the type of shader that does this is called a compute shader, and many more things. So the two things that we've already looked at, admin briefly look at it, was the vertex shader and the fragment shader. Those are the things that we briefly looked on, and I think in this article we are going to continue doing that. Okay, let's continue. It's also convenient to make use of lots of floating point number in this calculation. Can use them for positions in 3D, for values of colors, for timers, and lots of in-between variable we make up ourselves, like the intensity of light in our scene. You can see how the GPU hardware is going to be really helpful here, because the GPU can process many floating point instructions at once. You can guess why our shaders are designed to operate on only one item, the vertex, the fragment. So when we design our shaders, they are not meant to be used for many things at the same time. They are meant to be used only for one thing. They can be used for vertex shader or fragment shader or compute shader or ray tracing shader if that one exists. So yes, operate on only one item and not look over all of them. We are trying to make the most use of the GPU highly parallel architecture and run as many things at once as we can. Thus, each vertex reposition will invoke another vertex shader. Each fragment will invoke another of our fragment shaders, and the GPU can schedule as much as possible to run in parallel. So one vertex will call another, and yeah, this is a quick note. We don't need to know the details of GPU hardware architecture to start writing shaders for OpenGL. But as an aside, here is an overview. Note the term for each part differ by manufacturer. A GPU has cluster of processing cores. AMD calls these clusters compute units, and NVIDIA calls them streaming multiprocessors. These aren't really equivalent to your GPU's core. Each computer unit has a hierarchical organization comprising groups of processing elements. The processing elements are called shading units or stream processor. Some GPU also have specialized core clusters for AI and ray tracing. The shading unit, in turn, contains groups of threads that execute the instructions from your shaders. Threads are grouped into warps, also called wavefronts. There are usually 32 or 64 threads in a warp. Yeah, the warp runs the same instruction over all its threads, and each can use different data. So this is where the parallelism comes into play. Like a warp has, if it has 64 threads and is doing some calculation on float point, it's able to do those calculations in all these 64 threads, and it's actually pretty fast actually. This is called SIMD, single instruction multiple data. Lots of mathematics we will write in our shaders will make use of this to get a big speed up. You can learn more about how GPU work by following non-graphic GPU use. Official tutorial for AMD ROCm, HIP and NVIDIA CUDA. Anyway guys, let's continue. Like, look at this. This is a 36 vertices for a cube of triangles. 36 vertex shaders execute in parallel. Rasterized 2D triangles cover n pixels. N fragment shader execute in parallel. 7 fragments for this triangle. Colored surface, dynamic lighting, etc. Common drawing operations such as transforming each vertex and coloring each fragment can be done independently. We write a shader, a mini program to compute this operation, and the GPU highly parallel architecture will attempt to compute them all concurrently. Okay guys, I think I have to restart. Okay. Shaders Shaders are a way of reprogramming the graphic pipeline. This is what we call the graphic pipeline, these steps here. And shaders is a way, like we hook into the GPU pipeline cycle, and we change how the GPU is going to do his work. So this is very important to understand shaders. If we want to use a different coloring method for the cube in the image, or have an animated spinning cube, we could tell OpenGL to switch to use a different shader program. The rendering process has several distinct stages for transforming a 3D object into a final 2D image. So at first we give to the graphic pipeline a 3D shape, and it's about it goes from vertex transformation, rasterization, fragment operation, and at the end it gives us back a 2D image. We call this stage to process the graphic pipeline. So all the stages that the GPU takes from our vertex data to a 2D image is called the graphics pipeline. All of the stages of the graphics pipeline that happen on the GPU are called the hardware pipeline. So all of the stages that happen on the GPU is called the hardware pipeline, or programmable hardware pipeline. All the OpenGL APIs had pre-canned function like GLLite for driving the rendering model. We call this the fixed function pipeline. Fixed because it's not reprogrammable. These functions no longer exist, and we have to write the lighting equation ourselves in shaders. In OpenGL 4, we can write a shader to control many different stages of the graphic pipeline. OpenGL hardware pipeline. We said that the hardware pipeline, or the programmable hardware pipeline, is all the stages of the pipeline that happen on the GPU. Okay, so we have the CPU, GL draw arrays. It goes like this. Into the GPU, we have the vertex shader. Right shader to position each vertex. Animate. It's in the vertex shader that we program the position of the vertices on the screen. So it's also in the stage that we can animate. We can change the position dynamically according to an event. Maybe the mouse has moved, a button was pressed, a gesture, and etc. After the vertex shader has finished doing its work, we go to the tessellation control shader, optional stage actually. After the tessellation control stage, it goes like is the tessellator that does the tessellation work. After that, we go to the tessellation evaluation shader. It's also in the optional stages, but what those stages do is that it writes the shader to specific amount of new vertices to generate. Write shader to specify amount of new vertices to generate. Hardware unit that generates new vertex. Write shader to position new vertices. Like in these optional stages, it gives us the ability to write another vertex shader program, a mini program, to modify the previously vertex program that we have written. If I got it correctly, if I got it correctly, this is actually what it's doing. After these optional stages, we go to another optional stage, which is the geometry shader, optional stage 2. What it does is that write shader to generate or delete geometry useful for effect. Maybe we want to delete, like maybe when the player has crossed past the limit of the monitor, for example, we want to we want to remove or delete some pixels on the screen, and we don't forget that pixels are actually vertices. We want to delete some, and we want to, while deleting some pixel or vertices, we want to apply some geometry shape to maybe make it more, I don't know, like blurry, things like that. You know, geometry shader help us here a lot because it gives us the ability to modify our shaders. After these optional stages, we go to the clipping. Primitives are assembled, so triangles, primitives out of shot are discarded. Like, as I want to make a drawing to explain you what this phase is actually doing. This phase here, this phase, like the clipping. What the clipping does is that what the clipping does is that we have our vertices. We have our vertices. It goes, after the vertices has done, it goes to the tessellation phase. The tessellation control shader. It goes to this tessellation control shader. After the tessellation control shader, what it does is that here the shader that we write will specify the amount of new vertices to generate. It's optional, but what it does is that since this is optional, we can actually leave this. But what this does is that, let's say we have give it this point, 1 point here, 1 point here, 1 point here. What it's going to do is that what we want at the end is a triangle, right? But what OpenGL is going to do instead is that it's going to give us a shape like this, but it's actually multiple triangle that is going to be rendered, like multiple triangle, all the way multiple triangle. So at the end, we will not have a flat surface. It will be composed of triangle, and this is where clipping comes into play, because clipping will take this and it will try to remove all the part of those small triangles that are not meant to be rendered, and it's going to leave the other one. So we will come to this triangle to have this triangle. So this is the goal. This is where we want to be. So this is what clipping does actually. After clipping, we have rasterization. 3D primitive flatten into 2D shape. Is in the rasterization phase that we get from 3D shape to 2D shapes. Each shape subdivided into pixel size fragment. So what we are doing here is that since we gave him 3D, this was 3D, sorry for my drawing is with the mouse, so it's a bit difficult. This was 3D coordinate that we give him, but after rasterization, let me see, let rasterization, yeah, rasterization. I think I got it correctly this time. This is with an S. Okay. After rasterization, we go from 3D to have a 2D shape. 3D to 2D shape. And what it does is that each pixels, so each pixels is going to be, oh God, each pixels, let me see if I can, I think we are going to make a project that will help us draw with the hand. So like we do like this and it's drawing. I think we are going to do that because drawing with the mouse is very difficult. But each pixel is divided by what does it say? It's like each shape is subdivided by a pixel sized fragment. A pixel sized fragment, I think a pixel sized fragment is a pixel sized fragment, because I know that in OpenGL, since for color like this, we know that fragment shaders are used for color. For color, the color value are normalized to 1. It's a bit weird because we know that a pixel goes from 0 to 255, but in OpenGL it goes from 0 to 1. It's a bit weird, but I think it has something to do with this phase, this subdividing phase, because here after clipping we already have a triangle, but it's not colored yet. So we want to color it, so it goes to the rasterization phase. After the rasterization phase, we obtain a color thing, because, and this is the next phase, the fragment shader. The fragment shader, what it does, like we write shader to color each fragment actually. So I think fragment pixel, like pixel sized fragment are like vertices, but they are used to specify the length, the actual length of our shape. Yeah, the actual length. I think yes, fragments are used to specify the length. So guys, I think we are going to be a bit fast because the time, don't have much time, but let's continue. Yes, after the fragment shader, during the fragment shader, we write shader to color each fragment. Yeah, overlapping fragments are blended into a single pixel. It's logic. After the blending phase that we will, during fragment shader, there can be surfaces that are drawn, that are colored, and they are overlapping. We have the first surface and the second surface, and they both have been colored. So we want to join them. So it's called blended because we joined the two colors. Maybe they were colored with different colors, so we join them together and we obtain a new color. Yeah, this is the blending phase. Now after that, we obtain a frame buffer. So this is the final 2D image. So the final 2D image is attached to a fragment buffer. So when we get to this phase, we are done. I think what we did in our program, what are all these notifications? What we did in our program is that we simply did vertex shader, then we did fragment shader. That was all. But between this vertex shader and this fragment shader, they were clipping, there were rasterization. And after the fragment shader was done, the blending phase occurred or happened or had been executed. So this is it. So this is then what we call the pipeline. The OpenGL, like it is said here, the hardware or the programmable hardware pipeline. This is it. Yeah. So let's continue. A complete shader program comprises a set of separate shaders. So a complete shader program is a set of separate shaders, one to control each stage. We had how many stages? 1, 2, 3, 4, 5, 6, about 6 more or less. So we will have at least 6 shaders, mini program, small program. Each mini program called a shader by OpenGL is compiled, and the whole set is linked together to form the executable shader program. The whole, this is it. They are compiled together to form the whole executable shader program called the program by OpenGL. This is where we create the program. So this is why we created the program. We have declared the shader. Now we want the program. Is where we combine all the mini programs, all those other shaders together. This is it here. So yes, that's confusing. If you look at the quick reference card or further down the page, you can see that the API differentiates function into GL shaders and GL program. Actually, because GL shaders are not GL program. This is a GL create shader, GL source, and we compile. It has nothing to do with shader programs. It has nothing to do with that. Note that there is a distinction between a shader indicated by white boxes in the pipeline image above, which is a mini program for just one stage in the hardware pipeline, and the shader program, which is a GPU program that comprises several shaders that have been linked together. So the frame buffer is the actual shader, is the actual GPU shader program. So this is it. I think, guys, we have everything. We have everything. This is it. This is it. We have all we need. All. It means that if we go through this program, we are able to understand it properly. Because first we define our vertices. Then we define the vertex shader program to load the vertices. We create a 2D variable. In our main function, we create a variable using the vec4. The vec4. We pass that to the vec3 shape. And in the VBO, the vertex buffer object here, is in here that we are going to take the vertices. I think it's in here that we are going to take our vertices, our point here. This is it. We send the GL buffer data. We create an array buffer, the size of the element, and we are done. We can abstract this buffer size, data. Here we can abstract it, but I'll leave it like this. And after we have created the vertex buffer shader, we want a vertex array object, because it's the vertex array object that will be used by the shader actually. So we send the VBO into the VAO, and using the VAO we are able to create now the vertex shader here. You know, we take the vertex, we take the fragment, then here what we do is we create where the VA was, we create the shader program. After we've created the shader program, we use the program. Then we bind where our array, we bind the program with this here, and we draw the array. Simple as it is. Okay, anyway, let's continue. Each individual shader has a different job. At minimum, we usually have one vertex shader and one fragment shader per shader program, but OpenGL 4 allows us to use some additional shader too. Shader parallelism. Shader programs run on the GPU and are highly parallelized. Each vertex shader only transforms one vertex. If we have a mesh of 2000 vertices, what is a mesh? Mesh in computer graphics. What is a mesh? In 3D computer graphic, a mesh is a fundamental data structure that represents the surface of a 3D object. Yes, the surface. It acts as a 3D wireframe composed of vertices, edges, and faces. Vertices, points, edges, line connecting the points, and faces, polygons. So this is it. This is it here. This is a mesh. It's composed of vertices, the points, the edges, all these lines connecting all those points. So the points, the vertices, the edges, and the what was the last thing? And the faces, all these polygons. Yeah, all these polygons. So if you have a mesh of 2000 vertices, then 2000 vertex shader will be launched when we draw it. Because we can compute each one separately, we can also run them all in parallel. Depending on the numbers of processor on the GPU, you might be able to compute all of your mesh vertex shaders simultaneously. This is a table of comparison. Release date, GPU, NVIDIA, shader units, to the amount of shader that was able to run in 1 second at the same time, in parallel. Because there is a lot of variation in user GPU hardware, we can only make very general assumptions about the ideal numbers of vertices and facets each mesh should have for best performance. Because we only draw one mesh at a time, keeping the numbers of separate meshes drawn per scene to a lowish level is often beneficial, reducing the batch count per rendered frame. The idea is to keep as many of the processor in use at once as possible. GPU don't use batch. We will leave this for later. Difference between fragment and pixels. A pixel is a picture element, actually, because as I'm recording myself right now, you see me through image. An image are comprised of pixels, and pixels goes from 1 to 255. So it's logic that a pixel is a picture element. In OpenGL lingo, pixels are the element that make up the final 2D image that it draws inside a window on your display. A fragment is a pixel-sized area of a surface. A pixel-sized area. A fragment shader determines the color of each one. Sometimes surfaces overlap. We then have more than one fragment for one pixel. A fragment is a pixel-sized area. Pixel-sized area. So the size that a pixel occupies in the scene. A pixel-sized area. Yeah, pixel-sized area. So the size that a pixel occupies on the screen. All of the fragments are drawn, even the hidden ones. Each fragment is written into the fragment buffer image that will be displayed as the final pixel. If depth testing is enabled, it will pen the frontmost fragment on top of the further away fragments. In this case, when a farther away fragment is drawn after a closer fragment, the GPU is clever enough to skip drawing it, but it's actually quite tricky to organize the scene to take advantage of this. So we'll often end up executing many redundant fragment shader invocation. Yeah. Oof, guys. Looks like we've already taken more than 30 minutes and we still have a lot to go through. Maybe this is going to be the longest video. Anyway, we have this shader language. OpenGL 4.1 shaders are written in OpenGL Shading Language version 4.10.6. The GLSL OpenGL language from OpenGL version 3 and 4 are almost identical, so we can port between versions without changing the code. OpenGL version 3.2 added a new type of shader, geometry shaders, and version 4.0 added tessellation control and tessellation evaluation shaders. These, of course, cannot be rolled back to earlier versions. The first line in a GLSL shader should start with the simplified version. So we like OpenGL version 3.2 added a new type, the geometry shader, and the version 4.0 added the tessellation control and tessellation evaluation shaders. Those are only available to OpenGL 3.2 and 4.0. Each fragment shader starts with this version 4.410. The different version tags, if you were using 3x3, the minor, the major, the minor. Yeah, so it means that if we come here, the first line is hashtag version. It's like in bash, in bash you have to do something like this, bin bash, but in shader it's actually version, then we pass the version and we mark it at core. This is how we start a vertex shader, and this is what we did here. Then here we define it here. Anyway, let's continue first with the tutorial. OpenGL Shading Language contains the operator in C and C++, with the exception of pointers. Bitewise operators were added in version 1.30. Bitewise. Maybe we want to do multiplication, but we also want to do it doing bitwise operation is more faster. If you leave out the string tag, the version tag, OpenGL falls back to an earlier default. It's always better to specify the version. Actually, GLS data type. The most commonly used data types in GLSL are written in table. The most commonly used data type in GLSL are in the table below, or a complete list and the tables of function and operation available. See any of the quick reference cards and find GLS in the back page. Let's see what these cards looks like. Maybe we are going to download them. This is what OpenGL, yes, for our quick API quick reference. Yeah, this is actually a good thing to have. Maybe I'm going to download this and look at it later. Anyway, let's continue. Commonly data type: nothing, boolean, floating, 2D, 3D, 4D, points, color. This is a point, this is a color, and this is a direction. But why this is a point now? Why didn't we use 2D? Points and direction. Transforming surface, normal. Floating point, matrices. A matrix. In 4x4 matrix. A 2D texture. Stretching an image over your triangle. Yeah, look, like we have a triangle and we are able to put an image. This is cool. Yeah, this is cool. Stretching an image over your triangles. Yeah. Simpler cube. A 6-size texture, a skybox backdrop. Simpler 2D shadow. A 2D depth texture comparison, projecting shadows onto your triangles. File naming convention. Yeah, this is the naming convention. It changed. I use a different one here. Sorry. Each shader is written in a plain text and stored as a character arrays. It's usually convenient to read each shader from a separate plain text file. I use a file naming convention like this. The vertex shader for my text rendering shader program. The fragment shader for my text rendering shader program. The vertex shader for a particle system shader. The geometry shader. Vert is for vertexes, frag is for fragment, vert, yeah, for vertex. Geom is for geometry. Some coding text editor will do syntax highlighting for GLF if you add a GLS extension. The GLS reference compiler, GLSL, can check your shader for bugs if they end in vert or frag. So here we are going to rename this to vert because it's a vertex shader. And this is a vertex shader, that's why we rename it to vert. And nothing's changed. Expanding shaders with uniform and varying. GLSL is designed to resemble the C programming language. Each shader resembles a small C program. In Hello Triangle, we wrote a very minimal shader program that has only a vertex shader and a fragment shader. Each of these shaders can be stored in a C string or a plain text file first for convenience and then loaded into a string. Let's start from working the Hello Triangle program and modify it to add some new features. Recall that our vertex shader has the job of positioning any one of the vertex points from a vertex buffer inside the view area. It does this by assigning a value to the built-in GLSL variable GL. This is a built-in, yes. So GL position is a built-in GLS variable. So this is a built-in. This is not something that we made up. It's a built-in variable. The viewing area is actually a 3D volume with dimension -1 to 1 on the X and the Y, on the X, Y, and Z axis. This volume is called clip space. So the clip space is actually the viewing area, the view area, like the area where our triangle is going to be rendered is called the clip space. as any part of geometry outside it will be clipped off and not rendered. We can make our vertex shader program a little bit more fun by modifying our triangle position. If we use the current time as a variable, we can animate these two, like the current time as a variable. This is a variable. We can animate, right? Let's modify our vertex shader and add in a uniform for the current time. I won't add string quotes or line ending here. If you're not loading the shader from a file, you will need to add that. So here we define our vertex position, our uniform, a uniform. Let's come here. We don't have a uniform here. And adding a uniform for the current time. What is a uniform? Uniform is a keyword in OpenGL. What does uniform do in GLSL language for OpenGL? For OpenGL for that one. It's a keyword actually. In GLSL for OpenGL for uniform is a global shader variable used to pass read-only data from your CPU application to your GPU. Actually, uniform is like const. It's not going to be modified. So what? The 3D. This is the clip space. 3D clip space. The clip space or the volume. 3D volume. What we call clip space. Vertex 3D volume. Clip space. For our vertices. We do in vec3 vertex position. Actually, the floating time, the current time, the current time. Uniform is like const in C. Uniform. What is a float? It's a float time. It's a float time. Yeah, it's a float time. Then we have our main. We have our main function. In our main function, the position we will increase. Is going up and down, up and down, up and down. So vec3 position is vertex position, and we update position y with the function sin, with the time, the current time, and we set the GL position variable to be a vec4, that will take our position and take a 1. This is it. And get comes from outside the shader. This vertex position comes from outside the vertex shader. We assign it, modify its position with the scene function. We set the GL position variable to position. Reposition our vertices in the clip area. Yeah, so this is all the program. The input to a vertex buffer, the invariable, are called per vertex attribute and come from blocks of memory on the graphic card hardware memory. Actually, so the vertices are already in the graphic card, so they are just taken, called vertex buffers. We usually copy our vertex position into vertex buffers in our C program. Before running our main loop, we will look at vertex buffer in the next tutorial. This vertex shader will run on one instance of every vertex in the vertex buffer. You will notice the new uniform float time declares a variable. Instead of in for attribute, we have uniform storage qualifier here. Storage qualifier basically says where the data comes from or goes to. In this case, it will come from a variable in our C program that we will feed into OpenGL. The data type here is float, as we also know from C, and we've named it time. There is no rule here. Call it whatever you want, as long as it's not the same as a GLSL keyword. So int means that our value will come from vertex buffer in the graphic hardware memory. It means here that our vertices comes from the graphics hardware memory, also called vertex buffers. Yeah, this will come this time variable will come from our C program. Yeah, okay. Note, uniform in GLSL are actually constants in our shaders, meaning we can read but not change the value. In the Microsoft Directory, the API, they are named constants. I've also created a new vectory variable in our shader called post. I'm just making it a copy of the vertex position value from our vertex buffer to begin with. You can access the individual component of a vertex type like V3. A V4 has X, Y, Z, and W. Or alternatively, because these types can also represent colors, RGBA. On the line post, yes, I'm modifying only the vertical component of the position, not the plus operator. I'm using the built-in scene wave function to return a value between -1 and 1. That is handy because it won't move the triangle far outside the viewable area. I'm using the time value, which will be the current time in seconds, as the X value. the last instruction not that I'm using in our post variable for the final vertex position in clip space. Yeah, this is a scene wave. Hooking up C code to shader code. Yeah. So first of all, I want to read this. This one here, I will not ask AI, I don't want to ask AI. Okay. I will create a function. This file is getting detais error, and what does error shader? Let me just take this detais. Yeah. Actually, I have utils here. Okay. Then the create shader. Then the create shader. Okay. Guys, I'm just abstracting it because this file, look at this, is already 2,200 lines of code and I don't want it. This is just boilerplate code, so I'm just now in this. I want to create a new function called load. No, this is actually a F file. This is a header file called load. It's called load actually. It's called load. Load. It's not CPP, it's C. Okay. Nothing here. How? Okay. Load. What I want to load is that. What I want to do is I want to take a file path. I want to a constant car load shader. Then I want to take a constant car file path. This is what I want to do. It's going to load our shader and returns the value, so that in main here, what I want to do in main, what I want to do is that here where we were creating the vertex shader program, here I want to load this. Yeah, I want to change it to, I will create a going to be a constant car, and I'm going to call it load shader. I'm it's going to take, because it's going to be, I think it's going to be out, because yes, it's going to be in a build directory, it's going to be in outside shaders vertex shader program, going to be in the here. What we are going to do is that we are going to load the loaded file. This is simply what we want to do, and here what we are going to do, we are also going to comment it. So, and here I want, this is a fragment shader. Frag. Okay, fragment shader. I insert a new file. This is a fragment shader. This is a fragment frag. Yeah. This is a fragment shader. Okay. So first of all, I want to read So what I want to do here is that const a load shader const file path. We check if file path equals no. We return all first, simple. We return no. Simple. Simple as it is. Std simple as it is. And yeah, so what I want to do, I want to check if the file exists, but we know that if the file doesn't exist, file pointer f open file path read only. If fb is equal to null, we are going to do fprintf. I'm going to do fail to read the content of the shader file. For the shader file. Now I want it ftail. Like I want to do size t file size. I want this. Now I is ftail. What does ftail takes? It takes this. It takes this ftail. It tells us the length of the file. It tells us the length of the file. but before that F is fseek. Fseek the file, we start at 0 and we seek the end. We seek the end. We seek the end. We ftail. Then we rewind. We rewind. We rewind. Let's print this. File size. I think is yeah. Main. F vertex error, failed to load the vertex. Share a mini program. Definitely it's going to fail. I think yes, it's going to fail because it's going to return null. So let's compile this. Yeah, this is Are you sure? Are you sure it's a proper file? Anyway, let's see. Okay, like then I make a single. I will reuse this to allocate the we read the buffer. I create a buffer. The buffer is going malloc. Okay, the file times the size of character if buffer is equal to null. std fail to allocate amounts of memory. File size. Okay. So we have our buffer already. So we have our buffer. What we want to do with that buffer, I want to read at once. So fread, where you want to store in a buffer the amount, how many chunks you want to read. The count is file size, and where we want to read is this. So this is the red size. This is the red size. If red size is different from file size, the file size differs from the read size. Size T. Then, if everything is okay, we return a buffer. As simple as it is, we return our buffer. We read into the buffer at once, element size, the count. Okay. So this is 6. Let's try to run this to see if everything works well. But species and things like that, I think no, I think what I will do is file size. I will not, then here I will do read size, read size, read size, and this thing, yeah. Cool. As simple as it is, it means that we can also take this vertex fragment, yeah, in the main. Simple. Simple. Simple, simple, simple. Okay, guys. we've loaded the loading of our shader works. So hook up C code to shader code. If you compile and run your program at this point, it should still work without error and nothing should have changed. Why? It should still work. Ooh, ASCII illegal. The type is missing precision qualifier. OpenGL error could not link shader program. Illegal non-ASCII plot where missing precision. Is float 32 missing precision? Wait. Here in the vertex shader floats. The type is missing. Cannot be linked. The type is missing precision qualifier. The type missing precision qualifying OpenGL 4.1 using float type. To fix the missing error, you must declare a default position for floating point type at the top of your fragment shader. This is actually the fragment shader problem. Oh god, version 4 that pause and it will work. What's the problem again now? Now, illegal character. Where is the illegal character here? Illegal character. Where is the illegal character? I don't know. Let me identify if it's yeah, it's in the fragment shader that there's problem. Where is the illegal version? Or Anyways, let's finish first. Yeah, why uniform variable default to 0, and we are adding 0 to our triangle exposition. We need to modify your C program to update the uniform value. If you have not done so already, at the top of your while loop and add the following GLF function, you will get the current time. We've already done it. SDL tick. Tick. Yeah, this is it. SDL tick. SDL get tick. When our fragment is linked, every uniform value will be assigned a location number. Once our program is linked, here, down here, we use the program, we bind. Yes, when we bind this, we will use actually. We can use this to refer to its location number. We can fetch the location of the time uniform after the shader is linked. Call GL get uniform location using the shader program's OpenGL handle and the name you give the variable. If the uniform is not found by the name, then the value -1 is returned. This can happen if the name has a typo in it, or if the variable wasn't used and the compiler assumed it out. This is after the shader is linked. Yeah, after the shader is linked. After it is linked, current S outside. The current is the previous that is updated. After the program is linked, we get the program ID. Check for errors. Update the uniform value in the vertex shader. What we do is we call GL get uniform location. We pass in the shader program and the name of the parameter. Time lock. Location is SL3. No, it's a GL function. So we can use GL get uniform location. GL get uniform location, the shader program, and the name. We call the time. Now if the time location is -1, it means that, look at this, this can happen if there is a typo. So we'll do can't find in the vertex mini program. Then what I want to do is delete shaders. fragment. And since I destroy the context in the window, destroy the context, GL current context, SDL destroy the window, application window. Yeah, I do some cleanup, yes. Okay. Now, right before our call to draw the triangle, we can update the uniform to our shader using our current time and the location we retrieved. The location we retrieved earlier. The drawing section of our while loop now looks like this, with the addition of the function GL uniform 1. We clear here. We clear. God damn, I'm tired already, guys. GL def buffer bits. GL use program. We clear with the pink. Wait, is it really the triangle color? Be clear. Okay, nothing happens. So I don't even know why. Yeah, we use the program, we set the time location. Set the time location. So it's GL uniform 1. GL uniform 1. It takes the time, the location, time, location. Then the X value to set it from float parent S. We bind the vertex array, we draw the triangle. The GL uniform family of functions have variation matching all the GLF data type. Here I'm updating the GL float, so I call the one float, one for one float. If I was adding a vec3 uniform, then I'd call 3 floats. Look these functions up in the GL docs to see the full list and how the parameters differ. Note that I explicitly cast that times value to a float as it's a double normally. GL uniform calls operate only on the current bound shader program. So I called a new function after the GL use program. It won't matter if one shader program, it won't matter in our shader, but it will if you add another shader program. If you use OpenGL for them or newer, then you can use an alternative function family called GL, which does not have this limitation. Yeah, because the current bound is on the currently bound shader, so I called a new function after the bound. GL program uniform. What the GL program uniform does. This has to be. This must be after the bound program. GL use. Yeah. This is uniform 1F, the program, the location. and the value, the program, the location, and the value. Look at this. It takes the program, the location, and the value. It means that, what is the problem here? Let's first run it. It's not doing anything. It's not doing anything. It's not the current. It's the previous. Because it's the previous that gets updated now. Why is not going up and down? Why is not going up and down? Even now, it's not going up and down. What is the problem? What is the problem? Even so, what is the problem? What is the fucking problem? After we link the problem. Even so, what is happening? Get unit time is the time that I'm taking. Where I'm doing wrong. Yeah, oh, we create a shadow. We bind the shader, we get uniform location. Where I'm doing wrong. Actually, is 0. I have no problem with this. To that, I create a current. Yes, what we do. Clear. Location times location now. Oh, times location. What am I? It's not that. I'm pretty sure it's not that. What I'm doing wrong. What? What am I doing wrong? If I come here extended, I come up here. Jesus, what is the problem? Why is not updating? Okay guys, sorry, but I don't know why it's not taking. What am I doing wrong? Form location. Uniform location. After is bound. Use program. Use program. View. it's still 0. How? It means that this function don't take yes, the GL program unit form 1. One F. Shader program. There is a problem. It's not the elapsed time. So the current is, let's try with the current. Yeah, it's updating now, but the previous. But it's going too fast. It's going too fast. Too fast, oh, too fast, too fast, too fast. It's going too fast. It's going too fast. I don't know. We take this previous, the previous is updating. We take the current now. The current time, we take it once. Okay, we managed to get a bouncing ball, but it's not bouncing as we want. I don't know. It's a bit too much, you know. It's a bit too much. Like it's going up and down, and it's not good. Title countdown. Okay guys, I think we will leave off here for today, and we will come back tomorrow and we will continue looking at the problem and see what we can do to optimize the actual problem. So guys, see you later.